Alright, in this video we're going to look at more examples of mathematical induction. So this time we're going to look at problems that involve the summation notation. Just one guideline before we start working on the example, and this guideline says we will need to work out the first 3 terms of the summation. First 3 terms and the last term of the summation before we continue with the proof. So for instance, in A we have got the sum from I equal 1 to n of I. So the first term of this is going to be the term when I is equal to 1. So when I is equals to 1, it's going to be 1, and then the second term is when I is equals to 2, and then the third term is when I is equals to 3, and then the last term is when I is equals to n. So according to the proposition, this is equal to 1/2 of n into n plus 1. So basically this is the sum of the first n integers, sum of the first n integers, let's say the first n natural numbers. So natural numbers there. Right, so this thing is saying the sum of the first n natural numbers is equal to 1/2 n times n plus 1. So I want to prove this using mathematical induction. So we're going to start with step 1. Let's take n is equals to 2. Notice in this case that n is always going to be the number of terms on the left hand side. So when n is equals to 2, on the left hand side we're just going to have the first 2 terms. So 1 plus 2, this is equal to 3. Then on the right hand side we're just going to plug in n is equals to 2. So it's going to be 1/2 times 2 plus 1, and this is going to be 3. So the left hand side is equals to the right hand side, and hence the formula is true. Left hand side is equals to right hand side, and hence the formula is true for n equals to 2. Then step 2, which is the inductive hypothesis, we are going to assume that the formula is true for n equals to n. And so what we do here is simply rewrite this formula, and for every n we plug in k. So I'm going to assume that 1 plus 2 plus 3 all the way to k is equals to 1/2 k into k plus 1. So assume that this equals to that is true. Where n is an integer for some n equals to k, where that is actually k is a natural number. Okay, so then step 2 is done. Then step 3, we want to test whether so here we've done k terms. So for step 3 we're going to do k plus 1. So we're going to add one more term there. So we're going to have 1 plus 2 plus 3 all the way to k. Then we're going to add another term. The next term is going to be k plus 1. And then on the right hand side again, every k becomes k plus 1. So k plus 1 there, and then k plus 1 plus 1. So this thing is going to be equal to 1 plus 2 plus 3 plus k plus 1 is equals to 1/2 into k plus 1 times k plus 2, so that's k plus 1 plus 1. So I want to prove whether this is true. Is true. Provided that step 2 is true. And so the way we do this is we're going to notice that these terms here up to here are exactly the same as the terms we have there in step 2. And according to step 2, these terms are equal to 1/2 k into k plus 1. And so using that, we can write the left hand side as 1/2 k into k plus 1, then plus k plus 1. Then at this point we can we're going to factorize. We have got k plus 1 in both terms, so this is going to be 1/2 k plus 1. This term here we can write as, if we write it as one fraction, it's over 1 here, so it's going to be k plus 2. And so you're going to notice that this is now the same as the term we have got up there. Okay, so this is now equal to the right hand side. Then we say hence the formula is true for all values of natural numbers. Right, now notice here that there is a slightly different approach that we could have taken for this problem. I am going to do it in a different color. Let's use blue. So in this approach, instead of factorizing, we're just going to remove brackets. Okay, so here, so this is an alternative. So the left hand side is going to be 1/2 k into k plus 1 plus k plus 1. So this time we're going to remove brackets. So this is going to be 1/2 k squared plus 1/2 k plus k plus 1. So that's going to be 1/2 k squared. 1/2 k plus k is actually 3/2 k. So that's what we're getting on the left hand side. Then we go to the right hand side. So remember that the right hand side is this one here, 1/2 k plus 1 k plus 2. 1/2 k plus 1 k plus 2. So if we multiply out this by this, we're going to have k times k, which is k squared. We're going to have 2k plus k plus 2. So this thing is going to be 1/2 into k squared plus 3k plus 2. Then multiply through by 1/2. So this is going to be 1/2 k squared 3/2 k plus 1, and this is exactly the same as that. So we have that option to do there. Okay, so that's A. We are now going to go to B. In B we have the summation of 2I minus 1 from I equals 1 to n, and we are told that this is equal to n squared. So again, if we do the first three terms here, the left hand side, so when I is 1, it's going to be 2 times 1 minus 1, it's first term, and then for the next term 2 times 2 minus 1, and then for the third term there's 2 times 3 minus 1, and then for the nth term we're going to have 2n minus 1, and then on the left right hand side, that's what we have got. This first term here is going to work out to 2 minus 1, which is 1. This one is 4 minus 1, which is 3. This one is 6 minus 1, which is 5. And the last term is going to be 2n minus 1. All right, okay, so we notice that on the left hand side we have got odd integers. So actually this proposition is saying the sum of the first n odd integers is equal to n squared. Sum of the first n odd integers is equals to n squared. The other thing that we note here is that the numbers on the left hand side actually are NAP. So in this case, the question specifies that we are supposed to use mathematical induction. If it hadn't, we could prove this using the fact that it is an AP. So the sum is an AP. This is an AP with T1 equals to 1, D is equals to 2. So Tn, which is T1, n minus 1D is 1 plus 2 into n minus 1, 1 plus 2n minus 2. So this is going to be 2n minus 1, which is exactly what we have here. So that term there is just our Tn. So the sum, we can use the formula for the sum of an AP. So of course we have got n terms, so it's just going to be n. T1 is 1, Tn is 2n minus 1. So the terms inside the square brackets will simplify to 2n, and so this is just n squared. So proof complete. So this was in case the question does not say use mathematical induction. Well, in this case the question says use mathematical induction, so we're going to use mathematical induction. So let's work with n equals to 3 in step 1. So on the left hand side we're going to have 3 terms, 1 plus 3 plus 5, so this is going to be 9. On the right hand side we're just going to have 3 squared, which is 9. The left hand side is equal to the right hand side. Left hand side is equals to the right hand side. This implies that the formula is true. So that's the conclusion we come up with from step 1. Then step 2, we are going to assume that this formula here is going to be valid for some value of n called k. So we're going to have 1 plus 3 plus 5 plus 2k minus 1 is equal to k squared. So assume this is true where n is equals to k and k is equal to a natural number. Then step 3, we want to test whether so 1 plus 3 plus 5 plus 2k minus 1, this is term number k. So to get the next term, we take this term here and plug in k plus 1 where there is k. So we're going to have 2 into k plus 1 minus 1. Same thing on the right hand side where there was k, we plug in k plus 1. Okay, let's simplify this. So we're going to have 1 plus 3 plus 5 plus 2k minus 1 plus 2k. This is going to be 2k plus 2 minus 1, so it's going to be 2k plus 1, and this should be equal to k plus 1 squared. Alright, so to prove this again, we got to use step number 2. We can see from step number 2 that the terms up to here are equal to k squared. From step number 2. So that means the left hand side we can write as k squared plus 2k plus 1. Well, k squared plus 2k plus 1 we can factorize, becomes k squared, k plus 1 all squared, which is equal to our right hand side here. So the formula is true for all natural values. For all natural values of n. Okay. One more example perhaps. So this time in C we have got summation of 5 to the power I minus 1 from I equals to 1 to n. We are told that this is equal to 1 over 4, 5 to the power n minus 1. When n is equals to 1, it will be 5 to the power 1 minus 1. When n equals to 2, it's going to be 5 to the power 2 minus 1. When n equals to 3, it's going to be 5 to the power 3 minus 1. So when I is equals to n, it's going to be n minus 1, which is 1 over 4, 5 to the power that. Now, the first one is going to be 5, 1. Second one is going to be 5. This one is going to be 5 squared. So this time we notice that we are multiplying powers of 5. If we're multiplying powers of 5, this is a GP. And had the question not specified, use mathematical induction, we could prove this using the approach of GPs. R is equal to 5. The nth term Tn is 5 to the power n minus 1. So the formula for Sn is T1 minus Rtn over 1 minus R. So T1 is 1, R is 5, Tn is 5 to the power n minus 1. In the denominator we're going to have negative 4, in the numerator we're going to have 1 minus 5 to the power n. So this is the same as 1 over 4, 5 to the power n minus 1. Alright, however, for this question we need to use mathematical induction, and so that's what we will do. So step 1, let R be not Rn, let n be equal to 2, for instance. So it means on the left hand side we're going to have two terms. So it's going to be 1 plus 5 gives us 6 on the right hand side. Just plug in n is equal to 2 into that formula there. So it's going to be 1 over 4, 5 squared minus 1. 5 squared is 25 minus 1. It's 24 over 4. This is equals to 6. Left hand side is equals to the right hand side, and hence the formula is true. You can use formula or proposition. Then for step number 2, we are going to assume that the formula is going to be true when n is equal to k. We have 1 plus 5 plus 5 squared plus 5 to the power k minus 1 is equals to 1 over 4, 5 to the power k minus 1. Assume that this is true for some n is equals to k. K is a natural number. Then in step 3, we want to test or prove whether 1 plus 5 plus 5 squared. So these are all the terms from step 2. The next term is going to have k plus 1 there. And then on the right hand side we're going to have 5 to the power k plus 1. So all the k's are replaced by k plus 1. Now these terms are from step 2, and they're equal to 1 over 4, 5 to the power k minus 1. So the left hand side is going to be 1 over 4, 5 to the power k minus 1, plus this one simplifies to 5 to the power k. If I remove brackets, it's going to be 1 over 4, 5 to the power k minus 1 over 4 plus 5 to the power k. These two terms here have got a common factor. So if we factor out 5 to the power k, we're going to have 1 over 4 plus 1 here. And then 1 over 4 plus 1 is 5 over 4. So here we're going to have 5 over 4 times 5 to the power k minus 1 over 4. So this is 1 over 4 times 5 to the power k plus 1. These two we can combine because they have the same base. So this is 5 to the power k plus 1 minus 1. Alright, we're going to end here. The other two examples we're going to do in the next video. Yeah, so let's just conclude before So this is exactly the same as that right hand side there. So say this is equal to the right hand side, and hence the formula is true for all natural number values of n, right?